Consider sensing environments with sensors distributed in different positions. Each position provides a particular view on a phenomenon being considered for learning. Let's say human activity recognition like running or walking. How does the position of a sensor impact the learning process? How to isolate and temper this impact? And can we leverage prior knowledge about the structure of the sensing environment to improve the learning process? Learning in decentralized sensing environments involves learning local transformations that project the locally generated data towards latent spaces. The locally learned transformations are aggregated in a central server in order to conciliate the different views provided by the sensing environment. This interplay is repeated for many rounds until a consensus is found. The main bottleneck impacting the performances here is data heterogeneity across positions. The data generated by each sensor are biased by the sensor's relative position in the sensing environment. Using naive aggregation essentially flattens the data and leads to entangled latent representations and ultimately poor learning performances. Therefore, before aggregation, we have to get rid of the bias induced by the sensor's position. How to do this? The main idea behind our approach is to learn local transformations that are able to project the data into two mutually exclusive sets of components: position-specific components corresponding to the induced bias, and universal components that can be aggregated together in the central server. But can we do better? Can we leverage, for example, prior knowledge about the structure of the sensing environment to improve this process? The idea is to make the disentanglement process more effective and reflect the true underlying factors of variation in the data. This is what we propose here by representing the relative geometry of the sensors in an appropriate set of transformations, then enforce this additional knowledge during the learning process by imposing invariants of the universal representation across positions. We call this approach FedAbstract. We found that FedAbstract makes the disentanglement process reflect the true underlying factors of variation and improves training performances across a range of benchmarks. Thank you.